15th of November, 1943. Dawn breaks over Tarawa Atoll. Captain Philip Fleming stands on the deck of a converted barge, watching pumps force seawater through miles of copper tubing. He is an American military engineer, and he has built something the Navy said could not be done. The problem Fleming faces is simple and deadly. American forces are island-hopping across the Pacific, seizing coral atolls from Japanese defenders. These islands have no rivers, no wells, no freshwater sources. Troops land with canteens, but combat in tropical heat drains men fast. Within hours, soldiers collapse from dehydration. Within days, more men fall to thirst than to bullets. The Navy can deliver ammunition, food, and fuel, but water weighs too much to ship in the quantities an invasion needs. Fleming's orders are clear. Solve this, or the island campaign stops. Fleming is 38 years old, a civil engineer from Pennsylvania who spent peacetime designing municipal water systems. When war comes, the Army assigns him to the Corps of Engineers with the rank of captain. His background is pipes and filtration plants, not combat. But in early 1943, Pacific commanders present him with casualty reports from Guadalcanal and the Gilbert Islands. The numbers show that dehydration incapacitates men faster than enemy action. Field hospitals overflow with troops suffering heat exhaustion and kidney failure. Commanders ration water so strictly that wounded men go hours without drinking. The invasion schedule, carefully planned to strike one island after another, is failing because the human body cannot fight without water. Fleming studies the problem through March and April of 1943. He knows desalination exists. Shore-based plants in the Middle East and Caribbean remove salt from seawater, but these are massive industrial facilities built on land, requiring steady power and maintenance. The Navy needs something that can move with the fleet, operate in combat zones, and produce water immediately after troops hit the beach. No such system exists. Navy planners tell Fleming the engineering is impossible. Salt corrodes metal, pumps fail in seawater, boilers consume too much fuel. The equipment would be too heavy to transport and too fragile to survive rough seas and enemy fire. Fleming ignores the objections. He begins with basic chemistry. Seawater contains roughly 35,000 parts per million of dissolved salts. Human kidneys can process water with no more than 500 parts per million. The gap is vast, but the principle is old. Heat seawater until it evaporates, capture the steam, condense it back to liquid, pure water. The challenge is doing this on a floating platform in a war zone. He requests a barge, a flat-bottomed vessel 110 feet long and 30 feet wide, used normally to haul cargo in harbors. The Navy gives him one in San Diego. Fleming converts it into a floating factory. He installs a diesel generator to produce electricity. He mounts a boiler to heat seawater. He designs evaporation chambers where steam rises through baffles that trap salt particles. He adds condensers, long copper coils submerged in cool seawater where steam turns back to liquid. He fits storage tanks to hold the finished product. Every component must be compact, efficient, and able to withstand salt corrosion and the rocking motion of the sea. The first test in May 1943 fails. The boiler overheats. Gaskets leak. Salt clogs the evaporator. Fleming's team strips the system and rebuilds it. They switch to bronze fittings that resist corrosion. They add filters to pre-treat the seawater. They redesign the condenser coils to improve heat exchange. By June, the barge produces 10,000 gallons in a 24-hour period. It is progress, but not enough. An infantry division in combat consumes 50,000 gallons daily just for drinking and cooking. Fleming needs 10 times the output. He scales up. He adds a second boiler, a second evaporator, a second condenser. He increases the generator capacity. He tests the system around the clock, running the equipment until something breaks, then fixing it and running again. Engineers work in shifts, monitoring temperatures, adjusting valves, replacing worn parts. By August, the barge produces 100,000 gallons per day. The water is clear, tasteless, and safe. Lab tests confirm it meets all standards for human consumption. Fleming has his prototype. The Navy is skeptical. Admirals question whether the barge can survive towing across thousands of miles of open ocean. They doubt it can operate under combat conditions, with enemy aircraft overhead and shells landing nearby. They worry about fuel consumption. The desalination process requires burning diesel to heat seawater, and fuel is precious in the Pacific. Fleming responds with numbers. A single barge, towed behind a transport ship, can supply water for 5,000 troops. The fuel cost is less than the cargo space needed to ship equivalent bottled water from the mainland. The barge can start producing within hours of arriving offshore, long before engineers can establish a beachhead and dig wells. In September 1943, the Navy authorizes production of 12 barges. Shipyards in California and Washington begin construction. Each barge is identical to Fleming's prototype, built to his specifications. Fleming oversees the work, traveling between yards to inspect welds, test pumps, and train crews. Each barge requires a team of 6 men, a chief engineer, 2 mechanics, 2 operators, and a purification specialist who monitors water quality. Fleming writes the training manual himself, a 60-page document covering startup procedures, maintenance schedules, and emergency repairs. The first operational test comes at Tarawa. The atoll is a thin strip of coral in the Gilbert Islands, barely above sea level, with no vegetation and no freshwater. Japanese forces hold the island. American planners expect fierce resistance. The 2nd Marine Division will lead the assault, landing 18,000 men on beaches swept by machine gun fire. The invasion is scheduled for November 20, 1943. Fleming's barge will arrive with the second wave. Fleming does not go ashore. His place is on the barge, 3 miles offshore, beyond the range of Japanese artillery. He and his crew start the equipment at first light on the 20th. Seawater enters the intake pipe. The pump drives it through filters into the boiler. Steam rises into the evaporator. Condensed water drips into the storage tanks. By noon, the first 10,000 gallons are ready. Small boats ferry jerry cans from the barge to the beach, where Marines fill canteens under fire. The battle for Tarawa lasts 3 days. Casualties are heavy. The Marines take the island, but the cost is high. Fleming's barge operates continuously, 72 hours without stopping. The crew works in shifts, sleeping in 4-hour blocks, eating cold rations, monitoring gauges and heat that turns the barge into an oven. The equipment performs. No major breakdowns, no contamination. By the time the island is secured, the barge has delivered 290,000 gallons. Medical officers report that dehydration cases are significantly lower than in previous operations. Troops have water to drink, to wash wounds, to cool overheated bodies. Fleming's system works. Word spreads through the Pacific Fleet. Commanders request barges for upcoming operations. In early 1944, Fleming's design supports the invasion of the Marshall Islands. 4 barges operate at Kwajalein, producing 400,000 gallons daily. The system is refined. Crews learn to position barges in sheltered lagoons to reduce wave motion. They develop techniques for rapid startup and shutdown. They create backup procedures for when equipment fails. Fleming continues to improve the design. He adds a second generator for redundancy. He increases insulation around the boilers to reduce fuel consumption. He designs a portable version, a smaller unit that can be loaded onto a landing craft and brought directly onto the beach once the area is secure. This version produces 25,000 gallons daily, enough for a battalion. By mid-1944, the Navy has 40 large barges and 100 portable units in service. The invasion of Saipan in June 1944 proves the value of Fleming's work. The island is larger than previous targets, with mountains and caves where Japanese troops can hide. The battle lasts 3 weeks. American forces number 70,000. Fleming's barges supply water throughout. Engineers establish a distribution network, running hoses from the beach to field hospitals and command posts inland. Troops no longer ration water. They drink freely, wash regularly, and maintain hygiene that prevents disease. The difference is measurable. Hospital admissions for dehydration and heat illness drop by 60% compared to earlier campaigns. Fleming's system also supports non-combat operations. Construction battalions building airfields and roads require water for concrete mixing and dust control. His barges provide it. Hospital ships treating wounded need freshwater for surgery and sanitation. His portable units are installed on deck. The technology becomes standard equipment, as essential as landing craft and supply ships. In February 1945, Fleming's barges support the invasion of Iwo Jima. The volcanic island has sulfur springs but no drinkable water. The battle is brutal, lasting 5 weeks. Marines fight in tunnels and caves, in heat and ash. Fleming's barges deliver over 2 million gallons during the campaign. The water keeps men fighting. It saves lives in field hospitals. It allows the island to function as a base immediately after capture, with airfields and support facilities operational within days. Fleming receives the Legion of Merit for his work. The citation notes that his innovation directly contributed to the success of multiple amphibious operations. But Fleming does not see himself as a hero. He is an engineer who solved a problem. The recognition matters less than the fact that the system works, that men have water when they need it, that the invasion schedule no longer depends on finding freshwater sources. After the war, Fleming returns to civilian life. He works on municipal water projects in the American West, designing systems for desert cities. He does not speak often about his wartime service. The desalination barges are decommissioned, sold for scrap, or converted back to cargo haulers. The portable units are stored in Navy warehouses. then forgotten. But the principle remains. Fleming proved that water logistics could be engineered, that a critical vulnerability could be turned into a strength. His work influenced post-war military planning. Modern amphibious forces carry desalination equipment as standard. Aircraft carriers and submarines have built-in systems based on Fleming's designs. Humanitarian organizations use similar technology to provide clean water in disaster zones. Fleming dies in 1967 at the age of 62 in Pennsylvania. His obituary mentions his engineering career but says little about the war. There is no monument, no museum exhibit. The barges he built are gone. But in the archives of the Navy's Bureau of Yards and Docks, there are blueprints, maintenance logs, and operational reports. They show that between 1943 and 1945, Fleming's desalination barges produced over 50 million gallons of freshwater in combat zones. They show that his system operated in 14 major amphibious operations across the Pacific. They show that thousands of men drank water that would not have existed without his work. The lesson of Fleming's story is not about technology alone. It is about seeing what others overlook. Military planners focused on firepower, on landing craft and air support and naval bombardment. They saw water as a logistical detail, a problem to manage, not a factor that could decide battles. Fleming saw it differently. He understood that soldiers are human, that their bodies have limits, that thirst is as deadly as bullets. He built a solution that was practical, portable, and reliable. He did not wait for permission or consensus. He built a prototype, tested it, refined it, and proved it worked. In the end, Fleming's barges changed how the Navy thought about amphibious warfare. Water was no longer a constraint. Islands without freshwater sources were no longer off-limits. The pace of operations increased because troops could sustain themselves in places previously considered uninhabitable. The island-hopping campaign that brought American forces across the Pacific, from Guadalcanal to Okinawa, depended on many innovations. Fleming's floating water factories were one of them, quiet and unglamorous but essential. They kept men alive, and in war that is the measure of success.